In total, if everyone submit, there should be about 52 submissions. Okay, and the file name is your group number .pdf. All right, so I will try to comment over the course of the recess week. Our alpha demo is not until week 9, I believe, so still pretty long. And again, it is optional if you want to follow my comment or not. All right, so I will open it later today. The deadline for the submission will be Saturday. All right, and then I will start commenting during the recess week. So let's continue on about join first. Let's recap join. So we have a few joins operators. The easiest one is the inner join. If you want to preserve the dangling tuples, you need to use the outer joins. Okay, so if you remember the definition of a dangling tuples, then it's easier to remember which outer join you need to use. If you need to preserve the dangling tuple from the left relation, then you need to use left outer join. If you want to keep both, you need to use the full outer join. Okay, and then we have the natural join. Natural join is basically the condition itself is generated for you. And what natural join does is basically for all the attributes that are the same in both relations, the natural join will try to equate them. They must be equal. And afterwards, there's also a projection. Okay, so this projection operation is implicit in natural join. Because after you perform a natural join, the condition says that the attributes, they are the same in both the left relation and the right relation. So you have L, natural join R. If there are attributes that are the same, let's say L.A equals to R.A, you know that they must be the same, right? So that means you have duplicate columns. And because they are duplicate columns, you can remove one of them. So in the natural join, you just have to keep one of them. So the duplicated one will be removed. Now, natural join uses inner join. If you want to have a natural join that uses outer join, you can have natural left, right, or full outer joins. Okay? So again, you can actually omit the outer here, so you can have natural left join. Which means it's a natural, the condition will be generated for you, and it is a left outer join. Okay, so inner join is the easiest because it's basically just combine cross product together with the condition. So instead of having the condition as a selection operation here, which is corresponding to the where clause, you have it as part of the inner join statement, which is on the on clause. Then we have some examples. So let's go through some of the other examples, like for the outer joins. The definition of a dangling tuple here says that it's basically any tuples that does not participate in the join operation. You see that the result here, there are two of them, which means two from here did not participate, and two from here did not participate. Okay, and then you can figure out which one did not participate. Actually, only one of this. One of this did not participate. If you look at the column D, the one that did not participate is this, B. So this entire line is a dangling tuple. If you look at column A, 2 and 4 did not participate. So those are the dangling tuples. They did not participate in the join. If you want to preserve them, then you need to use the outer joins. If you want to preserve, so you have R and then some kind of joins with S. If you want to preserve from the left here, you use the left outer join. Again, the symbol is arrow to the right. If you want to preserve from the right, you use right outer join, and the symbol is arrow to the left. If you want to preserve both, it's bidirectional arrows. I couldn't find a better symbols for this. There is actually a symbol like this and this, but apparently they are already used for something else, so I can't really use them. Okay, so those are dangling tuples. So these are the dangling tuples, and these are the effect of using the outer joins to preserve the dangling tuples. A few things to note also is that because the dangling tuple has no counterpart, so if you look at the left dangling tuple, it doesn't have a counterpart on the right relations. So what you're doing is you fill them with nulls. Okay, and similarly for here, you preserve the dangling tuple from the right relation. The left part is filled with nulls. These are just definitions. You don't really need to go through this. You won't be tested on the definitions. But if you really want to know how it is constructed, you can go through this on your own. So yeah, there's an example here about how you can construct from the dangling tuple and the null values. You want to union with the inner join, but you need to make it union compatible first. Okay, so that's the key concept here. You need to make it union compatible before you can actually make it a union. Similarly, for the right outer join, the null will be on the left. So all you have to do is just reverse the order of the cross product. The null values will be on the left. The dangling tuple will be from the right. Okay, and that's what you get. There is some mistake here. I copy-pasted wrongly. This is actually the definition from the left dangling tuple. Okay? So this is the left dangling tuple. This is actually the right dangling tuple. So you should switch them. I'm going to upload the corrected version of this. It's basically just you need to swap those two. Okay? But the main thing here is that the actual effect, based on the definition, the full outer join, you can think of it as many things. It's a union of the left outer join and the union with the right outer join. Okay, and if you want to capture the dangling tuples only, is basically the left outer join with the right dangling tuple, or the left dangling tuple union with the right outer join. Okay? Or the last one, which is more important, it is actually inner join. You union with the left dangling tuple, and then you union with the right dangling tuple. Okay, the union here is critical, because some of the easier thing to mistake is that you may try to do this, which is totally wrong. Okay? Or you may try to do something like this. If you do not perform the union, then it's definitely going to be wrong. Okay? So if you look at the effect of this in particular, what you will get is basically that this one preserves some, this part preserves some dangling pointer from R, but those dangling pointer will be removed when you are performing this. Okay? So be careful with the order of operations. Okay, so let's go through some of the examples here. This has some very interesting property. What we want to do is actually pretty simple. We want to find the customers and the pizza that they like. Okay? But we want to include customers who don't like any pizza. Now, if you see this kind of keywords include something that do not have a counterpart, which means you need to use outer joins. Our first attempt is definitely going to be wrong because this definitely not going to include customer who don't like pizza because they are not even going to be there. Okay? And the output is basically exactly likes table. So our second attempt is to use the inner join. But again, if you use inner join, then you will not keep the dangling tuple. Okay, because you're not keeping the dangling tuple, this one will not work. So what you get here again is likes table. Pretty much the same as the likes table. One solution to this is to just use the left join. Now, the reason why we use the left join here is because we want to find customers who don't like any pizza. Okay, so the value that should be put as null is the pizza. And if you want to put the pizza on the right, so this one comes first, this one can be null. Right. Which means that you have to use the left join. Because you want to keep the right one possibly null. If you reverse the order, then you have to reverse the, you possibly may have to reverse the join. Okay? If you want to use a right join here, then you need to use likes L and customers C. Okay, so it depends on the ordering. But the effect of this is basically Willie here, which we actually retrieve from the customer's table, do not have any pizza that he likes. And because of that, the associated pizza will be null. Okay, so any questions on this example? The second example is find customers and the pizza that they like, include pizza that no customers like. So if you use the same arrangement that the name is on the left and the pizza name is on the right, our first attempt is probably try to use the right join. This one, in particular, is actually very, very interesting because notice that you do not get the result that you want. You actually get exactly the same as likes table, even though it looks correct. And the reason here is pretty subtle. Let me just illustrate with a PSQL. This cross product, all no, okay, wait. You inner join, left join, this one is right join. The first attempt. This one, did I erase everything? Yes. Okay. Okay, so that's basically likes table. Plus you have the null over here. Okay, the reason is that you should actually try this one. If you do this, notice that I'm just going to put a star here. This pizza, the first pizza here, comes from likes. The second one here comes from P, the pizzas. So this one is actually blank. All right? You need to choose the correct attributes. Okay, so remember that when we do this, okay, so when we do this, likes is on the left. That's a left table. Pizza is the right table. We want to include pizza that no customers like. So what we will have is that there's marinara here that no customer likes. But the associated customers, which comes from the likes table, is basically two nulls. If you try to project on this pizza, which comes from the likes table, you will definitely not get anything because this one is null. All right? So the error is very, very simple. The error is that instead of getting this from the L pizza, just get it from the P.pizza. Or, in other words, this one, after the renaming, you get from pizza 2. Okay? A very silent error. So, if you try the second attempt, which is pretty much the same, except that I'm getting it from P.pizza, then you will get the correct output, which is nobody likes marinara. Let me increase to okay? So when you do a join, be careful with the projections. Different projections may give you different result. So any questions on this? It's a very subtle differences, but it may affect the final result. Okay, so the next one. Here, we want to include both. Okay, and the easiest way is basically just use the outer join. Okay, and if you use the outer join and then you choose the correct attributes again, then you can just actually say there is a right join, full outer join. Okay, just be careful with the order of operations. But in the case of full outer join, it is actually, I forget the name, associative. Okay, full outer join is actually associative. So for any other join, left outer join, right outer join, they are not associative. For this one is associative, but the order of operations of this will be, this one will go on first. All right? And then the result of this, let's call it R, you will then full outer join with the pizza. And this is the part where I'm going to show you that this is actually equivalent to the union of the left join and the right join by doing this. Okay, this is the same. Because our definition of a full outer join is basically the left join, the right join, and then you just union them. If you want to be very, very complete, you can actually do the left join of all three of them first. And then for the second one, right join of all the three of them first, and then you just union them. Okay? So any questions? Natural join is, again, with a projection, and the projection just remove any duplicate attributes. Simple example will be basically something like this. For each restaurant, find its name, area, and the pizza itself. If at any point in time you already have a solution that involves either an inner join or a cross product where you try to equate the columns that are the same in both tables, that is a very good candidate to actually convert it to a natural join. Okay? Here, if you look at the restaurant table has our name, the sales table has our name. And those are the only two that are the same. And you try to equate both of them. So you can actually just use natural join. Like this. And then it will be much shorter. Okay, so any questions? Typically, what we're trying to do here is that the attributes that will be made to be the same will be, most of the time, primary keys. Okay, and if you do that, then natural join will basically preserve the uniquely identified. It will try to preserve as much as possible the primary keys, as long as the attributes that are the same, they are being equated, are the primary keys. If you want to try to figure out whether the result of a join requires distinct or not, because most of the time what we're going to do, especially in the midterm, is that output everything that is distinct. Okay, for midterm, you can just put everything with a distinct keyword at the end. But if you want to figure out very clearly which queries require distinct, which query doesn't require distinct, you can use the uniquely identify analysis. Okay, so that will be in more details when we talk about functional dependency. But let me give you a brief example. So let's say this one. Okay, and the question is whether the distinct here is necessary or not. So what you can do here is that this C name, as a primary key, uniquely identify likes. So what I can do is, I can write it as C name identify likes. Okay, that's the symbol for uniquely identify, which is the functional dependency. For the sales table, we have the R name, uniquely identify sales, all the attributes in sales. What it means is that every value of this is unique in L. Every value of this is unique in S. If you perform a cross product, which values will be unique? Okay, so it means that this one is unique. This one is unique. Every unique value of this will be paired with every unique value of this. So Cn, actually this one is not just Cn. This is pizza and Rn. I forgot that this is 2. Okay, so you have the R name and the pizza. Uniquely identify cells. Okay, when you do a cross product, that triples here will uniquely identify the cross product, right? Because you have a unique value for this, which will be paired with every unique value of this. So none of the triples will contain duplicates, by definition. And by definition, this triple will definitely going to be the key of the cross product table. Now, because the only way you can uniquely identify every tuple here is by these triples. Any subset of these triples cannot uniquely identify the cross product. And at the end, what we are trying to project on is just this. Right? We want to project such that only Rn remains. But Rn cannot uniquely identify the cross product. So you will need to use distinct. But if you try to query the triples here, give me all these triples, then you don't need to use distinct. Because the triple will uniquely identify the cross product. Okay? But again, for practical reason, in midterms, just use distinct keyword. I will not penalize for that. Assignment tree, I might, but if I'm penalizing for assignment tree, then I will clearly specify that. Okay? So yeah. So any questions on this? So again, for the last one is a view. View is basically not a table, but it is actually a virtual table. You do not really have a table corresponding to this. Okay? But view is basically generated from the underlying tables. The good reason for this is if you do not want anyone to have access to the underlying tables, you want everyone to only see the virtual table, then you can use view. All right? When we talk about the superclass and the subclass, the ISA, so this is the subclass. If the covering constraint is satisfied and you use the approach that only uses the subclass table, then you can generate the superclass as a view. Okay? The entity sets for the superclass corresponds to a view instead of a table. And that view will be the union of all the subclasses. All right? So yeah, to create a view, you need to give the query that corresponds to that view, because you create the view from underlying tables. The keyword is basically create view, and then the name S. So that will be a temporary, it's not temporary, it will be a permanent view, but there will not be any data that is stored over there. Every entry in this view will be generated by this query. Okay? So this query will be generated every time you query the view, or at least you can think of it that way. I believe I do have an example of it. So this is the view. Let's drop first. Enrollments doesn't exist. Okay, I need to recreate this. And then I can recreate the Oh, p.name. Is it? Okay, so now the view is created. You can query the view as if it is a table. So select star from course info. Okay? So view, you can actually restrict who can access the view. You can restrict who can modify the table. Okay? If you want to go into the full-blown database manager, you need to control who can modify the table, who can create table, who can query a view, and so on, and that is based on the role. Now, we don't really care about this, because when you install Postgre, you have one super user, which is the Postgres. If you want to have it more secure, you can create a new role. The keyword is create role. Okay, but it doesn't really matter. Okay, you don't really need to do that. This is another way to create a view, is that you can actually list down all the name of the attributes. It is basically an automated renaming. And why do we do this is because you want whatever the external user can view to be independent of what is the underlying database. Okay, so if they have any query that uses the view, it will not change. That query will not change. But how the underlying view is created will be changed. I mean, can be changed. Right, so here is your table. Your external schemas are your view. The physical schema, we don't really care. If you want to know more, it's on the level 3000 database. Okay, so that's view. It's basically just like a abstract kind of table. It doesn't exist, but there is a query related to it. Now, why do I mention view is because you're going to have practice before the midterm, which is your assignment 3. For midterm and assignment 3, I need you to give me the query as a view. Okay? So just create view with the proper name. I'm going to tell you what the name will be, but it's most likely create view question 1 as something. Okay? And yeah, so that's basically what you need to do for your assignment and midterm. That makes things easier to check, so that I can give you the test cases as well. The test cases will involve query on the view. And then whether you actually get it correct or not, you can look it up whether it gives you the correct result or not. Okay? So this makes things easier. So any questions? That basically concludes our lecture 5, and this is the summary as we have covered through it before. To remember this, what you need to remember is basically the middle one here is basically the non-dangling tuples. The one from here is your left dangling tuple. The one from here is your right dangling tuple. Okay, so which one you keep depends on which one you use, which joins you use. This one is definitely going to be a left join because you keep the left dangling tuple. This one is a right join. This is your full outer join. All right? This one we don't really care much because that's basically just keeping your dangling tuples. You can just subtract the inner join from there. Okay. So that's the end of lecture 5. Any questions? So let's have we do have quite a lot of things to cover for lecture 6. Let's just have a 5-minute break. Come back here at 4:45, and if you notice that I actually accidentally uploaded the full slide. So lecture 6_blank is actually the full slide. Yes.
Speaking about the assignment, I emailed you on Saturday. Sorry about that.
Uh-huh.
So afterwards, right, I could resume it, but the thing hanged, and then I carried closing with test manager. So
Okay.
it got like resubmitted, and I couldn't recover.
Okay. Have you already sent the template file? No. Okay. No. Then can you email me again? So is it because I don't usually check on you. Can you email me, and then I'll send you the template file, and just give me the template file back with all your answers.
Okay.
Yes.
So for the project,
Uh-huh.
front end can we use as a frame that
You can use anything.
so just build
Yes.
Also, those three are just recommended.
So I'm giving Node for Node.js because my idea was that if you do not know anything, you just need to learn fewer number of language. Because hopefully you kind of know JavaScript, or if you want the front end to be nicer, you need to use JavaScript anyway. Right? Python is because you should already have learned about Python in 1010s. But you can use anything. That one is just,
for recommendation.
yes, not really recommendation, it's just,
So can I use like MySQL instead
you,
of
you can,
so anything? Just
yes.
you just need to build a project.
Yes. If you're more comfortable with MySQL, PHP, and so on, just use that. The only restrictions,
Jungle.
sure. The only restriction that I'm giving you is that the SQL query you have to write yourself.
So we cannot use the.
So I think if you use Laravel, Laravel has kind of a query builder
Yeah.
which maps to the class, right? You should not use that.
Oh, okay.
Okay?
So,
Because this module is about database, you need to be able to write the SQL query yourself.
okay. I understand. So
And yeah, so if you want to use Laravel, just make sure that you know how to override those. Okay? Yes.
Just now in the lecture, right, when you explain the join, right,
Mhm.
because we're talking about like when the cross multiplication of R and S, right, but for likes actually it's customer name and pizza.
Oh, yes.
However, when you do the cross multiplication, right, does it
No,
mean
that okay. So, okay, that's my mistake. So this one should be C name and pizza. This one should be R name and pizza. If you don't have any other condition, it's C and pizza, R name pizza. But the pizza are the same. So those two values will be the same.
oh, so in this case,
Then just 3 of them is actually enough.
I see. But if pizza is not equal to this pizza, then you
No, then it because you can have duplicates
yeah,
there.
okay, understand. Thank you.
Actually, a quick note also, there's for this one, I was informed that I shouldn't make the table too small because I missed this particular underline. The primary key for likes is actually CNAME and pizza. So what you have is basically CNAME and pizza uniquely identifies likes. You also have RNAME and pizza uniquely identify cells. So when you do a cross product, the only tuple or tuple that uniquely identify L cross S will consist of all 4 of them. So L.pizza, Rn, S.pizza. You have all 4 of them. However, we have this. S.pizza is always equals to L.pizza, which means any of these 2 values will always be the same. And that is the only reason why you can, because these two are always the same, you can then reduce it to Cn, pizza, and Rn. Okay? Without this condition, then you cannot reduce it, because the pizza might be different from the other pizza. Okay? And this actually kind of illustrates the natural join more clearly, because if you do the natural join, the pizza will be this, right? Will always be the same if you use natural join. In which case, then, if you use natural join, you will always have that merging. Okay? So yeah. And I believe when we talk about functional dependency, most of the joins that we talk about will be on the natural join. So that's minor thing that was it my, yeah. Unless this was my example. If this was my example, then it's correct. But if this was my example, then I missed that underscore on the pizza, which I think I used this. Okay, so anyway, lecture 6. So this is more on SQL query. So far what we have discussed, even with the join, let's term it as a simple query. This is especially with respect to the project when I ask you to have the interesting queries, and those interesting queries have to be complex queries. So it pertains to this SQL3 topics. Okay, so this, I think we'll just skip it. The first kind of complexities that we can achieve is through this thing called the aggregate function. This does not really have any counterpart on the relational algebra. Okay, so you can't really write this down as a relational algebra. This is basically, you want this function to look at collections of tuples and figure out something about them. For instance, if it involves number, you can find the average, the minimum, the maximum, or you just want to count how many of them there are. Okay, and this can be used in a lot of places, in the select clause, in the having clause, and the order by clause. The last two we will be discussing in this lecture. So these are the lists of aggregate functions. The bottom one is what happens if there is any null values, or if there is or if the relation is actually empty. Okay? When you do a count on empty relation, then it's simply just 0. But if you want to find the maximum and the minimum is actually null. You do not know what will be the maximum value of an empty relation. And as long as you have any null values, the minimum and the maximum will be null. Okay? And that is because any operations on null value give you null. So if one of them is null, then you get null, basically. Okay, so this is an example of an aggregate function. So you can actually just read this on your own. The meaning is actually pretty straightforward. Okay, so it's just the minimum, maximum, average, and sum, or count. Just note that for counting, it is only counting the non-null values. Right, so aggregate function. So this is the simplest example. Find the number, the minimum price, the maximum price, and the average price of pizza sold by Corleone Corner. Okay, so you can just fill in the blank. The minimum can be found using the minimum function, aggregate function. Okay, maximum is max, average is AVG. Okay, so that's the color coding. The number here is just the count. Okay, so that's aggregate function. It's kind of the easiest out of the rest. But the main thing here is that how do you count this? Because I can make it more complicated. I can make any of this aggregate function more complicated by actually performing a grouping. Grouping can be done in an order by clause. So what does grouping mean? So before you perform any aggregate function, you can actually group the tuples. Right? The table can be separated into several groups, and the aggregate function will only be applied to that groups. Okay, so the order by clause is for you to create that grouping. So let me show it by example here. So if you want to find this example, oh, actually no, sorry. That is the group by. The order by is just sorting. Right, sorry. It's 5 p.m., so my mind is pretty tired. Order by is for sorting, okay? And you just need to sort whether it's ascending or descending. And that's it. If you want to sort the pizza in ascending order followed by customer name in descending order, you just have to list them sequentially. So the pizza first. So you order by pizza, and then within that pizza, you will order by customer name. Okay? This will do the sorting by itself. If you want practice, you can actually try to do the assignment one using SQL. You will see how much easier it is in comparison to whatever you wrote. Except maybe for that one person who wrote things in batch script, the bash script. That was like the easiest solution I've ever seen. But yeah, for the rest of you, especially if you use Java or C, you will notice how much simpler SQL is in comparison to your program. Now, in the order by, because you're ordering it, you can actually limit how many results you want. Okay? So this is kind of like if you go to Google, Google only show you like the top 10 or top 20. If you want to look for more, you go to the next page. Okay? And this can be done using the limit keyword. You limit it. You want the top 10, then just limit it to 10. Okay, and for this case, it's just the top 3 pizza. Then just limit it to 3. Okay? The offset is that because you limit it to some value, the offset is just shift everything. Okay, so for the offset, you want to show everything except the top 3, then just offset it by 3. Like this. Right? And you can combine them. You can combine them in the sense that you want to find the 4th and the 5th most expensive pizza. So that's a limit of 2, but you exclude the first 3. Okay, so the limit is 2 and the offset is 3. Okay, so in the case of you want to show all the result, but in different pages, then for every page you can have, let's say you want to limit it to 10, then you can just say the limit is 10, and the offset is page number times 10. All right? But you must start with 0. So you can say that page num times 10. If your page number starts from 0, then this will give you the result in a page-by-page basis. So if you're at the page 0 of your query result, you will show only the top 10. If you click next on the next page, then you can query that the page number is now 1, and then this query will just give you the next 10. Okay? So that's one way. And that is kind of more efficient than if you get all the result and then you do the cutting on the front end itself. This is the part where the group by is. So if you want to perform the aggregate function, but only on selected groups, then you need to use the group by. Okay, so what the group by does is that for every column that you are trying to group, that group will have the same for all that columns. Okay, for instance, you want to find that for each restaurant here, you want to find, using the aggregate function, the maximum and minimum price of its pizza. Okay, so the maximum and minimum price is given by the aggregate function. Because it is given by the aggregate function, if you do not use the grouping, the aggregate function will be used on the entire table. You will find the minimum from the entire table and you will find the maximum from the entire table. If you use a grouping, the minimum and the maximum will be only for that particular table, for that particular groups. And this one we are grouping by restaurant name. So conceptually what we will have is that we will have this grouping. Right, so you partition it by the restaurant name. So this is the first group, this is the second group, this is the third group, fourth group, and the fifth group. If you apply the minimum and the maximum aggregate function, they will only apply to each particular group. So this one will give you 19 and 25. This one will give you 16 and 16, 23 and 23, 22 and 22, 17 and 21. Right? Without the group by, what you will get is basically only one value, which is 16 and 25, which is the minimum of the entire table and the maximum of the entire table. Right? So when you compute the minimum and the maximum, you will do that for each of the group, and this is what you will get. Okay, that's the conceptual view. Now, before I show you the code using the group by, there are other ways to solve this, but it will be very, very bad. And the way to solve this is basically you perform a union. Right? This is one group where the name is just Corleone Corner. This is the second group where it's just Gambino Oven, and then you need to have the third group for this, Lorenzo Tavern, Mama's Place, and Pizza King. Okay, but as soon as the number of restaurants increase, if there are more restaurants named, then you need to change your query. Okay, that's not scalable. So what you can do is you can create this grouping automatically using the group by clause. And this is basically just the grouping by our name. Okay, so if you run this, then you will get this exact result. Okay? Any questions? So again, another example is that for each restaurant, find average price. Okay, and then we can combine this with the order by, because there's a descending order of average price. Now, but because we need to say that we need to order by the average price, we need to name this. Okay? Once we have named this, then we can use that in the order by. Okay, so any questions on this? The next example will be this. You can group by with two tuples. Now, for this grouping, the department and year. Right. So the grouping will be this and this will be in one group, which is the group of 1 CS. This will be in one group, which is 1 engineering. This will be another group, which is 2 engineering. This will be another group, which is 2 CS. Okay? And that's why the count for this is the only one with 2. Any questions? So that's the group by. The group by will just create that grouping. And then the aggregate function will be applied to each of the grouping individually. There are some restrictions. So this is what group by means by the same group. You use the is not distinct. Okay, they are only in the same group if the series of this, if this expression evaluates to true. And remember that you use is not distinct. So null values is considered distinct from, null values is considered not distinct from other null values. Okay? So for this particular one, the grouping is A and C. So this one is one group. Because the null and the 19. Null is not distinct from null, 19 is not distinct from 19. This one is also another group. This one is another group. Okay? So there are 4 groups over here. And then for each of these, you output each tuple correspond to one group. So if you have any operations, any aggregate function involving these groups, it will be applied individually. Like if you try to find the max C, actually no, that doesn't make sense. If you try to find the maximum of value in B, this one will be 2, this one will be 20, this one will be 2, this one will be 18, right? Because that's the grouping. Okay, so is it clear so far? There is a restriction, and this is the restriction that I'm telling you, is that this condition must be satisfied. Okay, because you're trying to group something. And the grouping is there, the group by is there for you to perform aggregate function. Okay, so if the aggregate function actually crosses that boundary, then it kind of not make any sense, right? So this condition basically try to prevent that. It is actually easier to just give you an example. So let's say for this one, right? Is this a valid grouping? Okay, so you look at each of the conditions. For each column A in relation R that appears in select. So you see there's department, there's year, and there's count. Count has everything. Okay, the column is everything. Okay, so column A appears in the group by clause. This one appears in the group by clause, so this one is okay. Column A appears in the aggregate expression. This one is okay. This one does not appear in here. And this one is also not the primary key or candidate key. Okay, so this one is not okay. Okay, so that's an invalid query. Okay, so any questions? Now, the other condition, because I have 2 conditions, right? The other condition is this. If an aggregate function appears in select and there is no group by clause, then the select must not contain any column that is not in the aggregate expression. Okay, so if you look at this one appears in select. The select must not contain any column that is not in the aggregate expression. Okay, so this one contains price. Wait, not that one. This is the R name. Sorry. You look at the R name. The R name does not appear in the aggregate expression. Okay? And it doesn't appear in the group by as well. So this one is possibly invalid by this condition. But if you look at the previous condition, it is actually accepted because our name, is it? No, self. So it's not accepted because our name is not a primary key in self. The primary key in self is our name and pizza. Okay, so this one is invalid. But this one is okay. If you only have aggregate functions, it's fine. As long as the select doesn't contain any other columns that doesn't appear in the aggregate function, then it's fine. But what it means is that you're just finding the minimum and the maximum from all the tables without doing any grouping. Okay, so that's the group by. And then we can look at some examples that we can try to solve. So this was done before. This is just the conceptual view of it. So this is the query, and it corresponds to each of this conceptual view. Okay, so if you want to find each restaurant, for each restaurant that sells some pizza, you want to find the name, area, and average price. What you need to do is you need to get all the restaurants first that sells some pizza. And that you can only get from the sales table. And then you join with the restaurant table. Why do you need to join? That's because you need to know the name. All right? So once you do that, then you can partition by name, which is the group by operation. And then you do the aggregate. All right? Any questions? The next kind of clause that I'm giving you is the having clause. This is actually conceptually simple. If you want to find restaurants, like if you look at this example, then the easiest way to do this is basically have a where clause that says that the average price must be greater than or equals to 22. However, for some weird reason, SQL does not allow aggregate function to appear in the where clause. Okay? Which means that having clause is just replacing the where clause but for aggregate function. If you try this, you will get an error. But if you replace it with this, it's fine. Okay? That's what having clause is. It's basically because SQL doesn't allow aggregate function within the where clause. The property, again, is very similar to the select clause. Is basically just doing this condition is basically exactly the same as that group by clause, except that you replace the select with the having clause. All right? Because again, the having clause is just because you need aggregate function to appear in a counterpart of the where clause. So it follows the same restrictions as the select. Now there is an easy way to conceptualize all of this if you write your SQL query like this. All of this is from top to bottom. This is how it is going to be computed. Well, not necessarily, but this is an equivalent way of computing this query. The actual computation may be different, but whatever computation your DBMS is using, it must be equivalent to this computation. All right? The DBMS may do certain kind of optimization, but the final result is as if you are doing this kind of computation. All right, so you can try to read up on this. This is kind of an equivalent query, but this is how you can think of it like this is how a default implementation of DBMS is going to operate. If you create your own DBMS, you need to make sure that it is equivalent to this. But because you're not implementing a DBMS, then what you need to know is that any implementation will be equivalent to this if there are no bugs. Okay, if there are any bugs, then it might be different. All right? So any questions? The next part is what we call a subquery. Subquery is, so a query is basically, think of a query as a simple query of select from where. A subquery is that select from where appearing in places that you don't expect it to. Okay? It can appear anywhere. So if you have a select from where, you can have an inner select from where appearing in the select clause, from clause, or where clause. There are restrictions from all of this. Okay? If it appears in the select clause, it must be a scalar subquery. If it appears in the from clause, it's called a common table expression. If it appears in the where clause, you need to use this keyword. If you have a note from previous semester, we include one more, which is unique. But unfortunately, unique is not implemented in Postgre. Okay? So that's why I am excluding it from this. If in your project you use other kind of DBMS, then you can use unique if you want. Okay? But for midterm and assignment, you are not allowed to use unique because it is not supported in Postgre. Okay, so let's start with the scoping rule first, because we have what we call an inner query and we have an outer query. So it is basically kind of like if you have a nested function. Remember, if you have Python, you have a nested function. So the scoping rule is kind of similar to a static scoping in a sense that you can actually access the table alias from outside. Right? If you're inside the query, you can actually use it from outside. It is easier to demonstrate this with example. Okay, so the first one here, it is definitely okay because you already named this as this. Okay. In fact, the only one that is not okay is this last one. Right? Because they are supposed to be at the same level. They are not at the inner one, so you cannot actually access from here. Right? So this is going to be critical in our example of the CTE later. The common table expression is invented simply because this one is not allowed. Right? So let's start from the very simple one, the select clause. If the subquery appears in the select clause, it must be a scalar subquery. What a scalar subquery means is that it is at most one tuple with one column. Because at most one tuple with one column, you can actually just get the value directly. It is scalar values. Or we also say it's as atomic. It is not a table anymore. So this one is a scalar values. This one is not. Because you have two columns. Right, so this one is wrong. It is not scalar values. This is what you can do with the subquery. Okay, so you can use the subquery. So the one in blue is your subquery. It appears in the select clause, but it is guaranteed that it will only have one tuple with at most one value. Okay, it may not have any value, in which case the value will be null. If it has a value, it has at most one value. Okay, so the question is, how can you check whether it only has one value? Again, we can do the distinct analysis from before. You can check that this one, restaurant, the uniquely identifying attributes is our name. If you restrict the our name into a single value, the output that you will get is only a single value. All right? Because it uniquely identifies the entire table. It's a primary key. So yeah. Any questions on this? Now it's just that unfortunately for this particular example, you can solve it without using the subquery. In the case of projects, you need to make sure that it cannot be solved with a simple query first, before treating it as a complex query. Okay? You do not make it complex for the sake of making it complex. Okay? It has to be really, really complex. So yeah. Any questions on this? Subquery in the select clause is the easiest, because as long as it satisfies the scalar subquery, it's fine. If it appears in the from clause, it's called a common table expressions. Okay? It is common because you can use it in the subquery. The syntax here is that it's with something as something. Okay, this is the name. This is the name of the common table expression, and this is how you generate the common table expression. The thing about this is that if you remember the relational algebra, in our relational algebra, we kind of split things. If the relational algebra expression is too long, you can chop it up, right? It actually corresponds to these common table expressions. So if you have the result as something, Q answer, that involve, let's say, Q1 cross Q2 with some kind of conditions, and Q1 was generated from something, and Q2 was generated from something, you can use the common table expression with Q1 as that query, comma, Q2 as that query, and then you go on with the query with the Q1 cross Q2. Okay? Yeah, never mind. Ignore that thing. Okay, so in the case of midterm and assignment and project, I'm going to limit the use of CTE into at most 2. Because the reason is that this makes the SQL to be imperative. In the sense that you perform this computation first of Q1, and then you perform this computation of Q2, and then you perform this. But the idea of SQL is not to make it imperative, it's to make it declarative. You do not care how it is going to be computed. You just want to describe what is the final table look like. And the CTE is not the way to do that. It basically makes it to be imperative. So if you really need CTE, I'm going to limit it to at most 2. All right? So we had this case last semester with people having about 5 or 6 CTE. And if there's a mistake on that, especially in the midterm, it is very, very hard to give partial marks. Because if the mistake is just small, but it's somewhere in the middle, then it's not exactly clear how much the student understand. Right? So that's why this particular semester I'm going to limit it to at most 2. Okay, so that's what CTE. And the last point there is that we're not going to cover it. It can use for writing recursive queries. Let's have an example first. This is our given relations. Let's say you have courses and you have enrolls. You want to find this, right? This illustrates the kind of use of CTE. So we want to find the count for the database system first, and then we want to compare the count with something, right? The code looks something like this. This solves the problem without using CTE at all. Okay, but you have subqueries in a lot of places. Okay, some of the subqueries you may actually remove, but the main thing here is that you do a natural join between C and E. You also do a natural join between C and E here. It is kind of duplicated. If it's not exactly very clear, but it is actually kind of duplicated, especially if you rearrange this. If you rearrange it this way, the only difference will be the select here, as well as the, not the group by the where. Okay? But if you have already computed this, you can actually compute this from here. Right? You just have to restrict it further that the C name is equals to database system. Okay? In particular, you can try to replace this with whatever that is, right? X. But as we said before, at the start, based on the scoping rule, you are not allowed to do this. Okay, so if you try this, you will see that X is not present. Okay? So we cannot do this. Actually, there's an intermediate one that is missing. This one you can do it, but if you just replace this with X here, that one is not going to be accepted. Okay? So you cannot do this except if you use CTE. If you use CTE, now the name X here can appear over here. All right? So that's some possible use of CTE. Any questions? Yes? It's a good question. View will be a separate query. Right? The way we're going to do this for the midterm and the assignment is that your output, your answer must be a single query. A single query is one that is terminated by a semicolon. If you create a view, an intermediate view, there will be a one semicolon in itself. Right? So then if you use it here, then you have two semicolons. Okay? So for midterm and assignment, you are limited. Your answer must be a single query. You are allowed at most 2 CTE. Think of it as 2 views. Okay. Any other questions? So the last place where the subquery can exist is in the where clause. Okay, we have 4 possible keywords for that. The first one is exist. The second one is in. The third one is any. The fourth one is all. Exist only checks for existence of a value. In, it must be exactly 1 column, and that value can be compared with the scalar values, and then it must be exactly that, within that. So it's not just checking for existence, it is checking whether this value is within this. It's a not subset, but it's a set inclusion. It's basically this symbol. You're basically checking some value is in the set S. For the exists, you're basically checking that this one is not equals to empty set. That's it. Okay? The problem will be if you have empty. For exist, it's simple, right? Because you're checking whether it's not empty. So if it's empty, then just return false. If it's in, then just return false, because it cannot be inside. Now, for this, any and all, any corresponds to the or keyword. Okay, so if you say any, it means that any of this is true. A or B or C or D and so on. Okay? And then all is corresponds to N. So again, it is A and B and C and D and so on. The problem will be if there's emptiness there. This one, there really is no logical explanation except that is the standard. I believe the other language that has this is kind of like Python. Right? Python has some kind of or and then and. That or if you do any kind of functional programming language, they have the or function and they have the and function. If you try to do an or on an empty without any argument, typically the result is false. If you try to use and on an empty without any argument, typically the result is true. Okay? If you do that, I believe there's a very nice connection between that and the tropical semi-ring. But in this particular case, just think of it as if it's empty, just false. Okay? There's no reason why it has to be true. There's no reason why it has to be false. It's just that's the standard that we define. All right? Which means that you cannot have any relation between this query and the currently known semi-ring if you learn about group theory. Right? But just treat it as a convention that if it's empty, it must be false for both. Okay, that's it. Now, this will be very, very critical if you try to use not. Okay? Because if the result is empty, if you try to not it, you will get true. Then you may get everything. Okay, not false is true, right? So be careful with that. So yeah, so the rest is actually just examples. So if you want to do this without the use of this simple query, you can actually check. Okay, so this one is kind of like exists, right? So find customer who like some pizza. So if you can try to find a sub-query where you have a customer name, like something by Corleone Corner, likes pizza by Corleone Corner. If you can have this sub-query, you can check whether the sub-query is empty or not. Okay? So that's the main idea. If you try to use exists, and it translates to something like this. Okay, this one can be any values. Because what you want to check is an existence of that value or not. Okay? And this is where you connect the pizza. You connect that this particular customer likes this. So any questions? You can invert it such that it's not exists. So this is typically the kind of queries that you want to answer. For a not exist, you have everything except. Okay? And the except is exactly from the exist. Right? So you can just actually subtract the exist, and then what you get is basically not exist. Okay? So let me repeat. So you have this. You have this query, which is, okay, you have this query which is, can be converted to an exist if you have exactly the same query for exist, but you want to remove those. Right? So you want to subtract from this exist, then you can simply just use the not exist. Okay, so if it's empty, then you get true. If it's not empty, you get false. All right? So there's a exist, and the counterpart is not exist. The in, there are multiple usage of this. The simplest example is basically to check whether the value is within another tuple. You can specify a tuple like this. Okay, so if you want to find all the pizza that contains ham or seafood, rather than having the union or having a more complicated where, you can actually check in here. Okay, it's just basically shortening it. Now, this tuple need not be fixed. It can be generated by another query. So then you can get something like this. Okay, so it is still, again, the same tuple, a similar tuple, but this tuple, instead of being fixed, it is generated by a query. Okay, so here, what you can do is you can find all the pizza that is sold by Corleone Corner, and then this pizza must be inside that. And again, the restriction applies that it must be a single column. So there must be only a single column over here. Okay? Now the any and all is basically you try to convert it into that long OR operations where any one of them can be true. If any one of them is true, then you return true. Right? And it can be used to solve this problem. This one is basically finding restaurant that sells more expensive pizza than some pizza by Corleone Corner. Okay, so you can try to do the operation of this. Right? And this one we're solving it without the any. The identifying feature here is that when you compute the exist, right, you are computing it multiple times for all the tuples. Okay, and then you check whether there is any result or not. And then the result, you just give it as a value 1. What any keyword can do is that you can convert it such a way that this operation is taken out to be outside over here. Right? So what we have is that the price here is greater than any of this. This is the operator greater than. So let's call this P, and let's call any of these values. Let's get all the values that is generated by this is P1, P2 until Pn. Okay? So assume that the any, the subquery within the any, generates this result. So the actual output that you will get is basically something like P greater than P1, or P greater than P2, or, and so on, or P greater than, greater than Pn. Okay? So instead of using exist where the subquery can be computed many times, this one, you can just compute it once and then you compute this. If any one of this is true, then you return true. Okay? So that's why it's kind of like asking you, it is more expensive. It is P greater than some Pi that is sold by Corleone Corner. So you generate all the price of all the pizza that is sold by Corleone Corner, and then P, there exists Pi such that P is greater than Pi. That's what it means. Okay? If you do a subtraction, if you do a set difference on this, what you will get is basically the most expensive pizza. Okay? So here, our idea is, okay, so price here is again still P. The result from here, let's say, is P1 up to Pn. You want to check, for this sub-expression, you want to check if this price is lower than some other pizza. If there's any other pizza that is more expensive than this. So P is smaller than P1, or P is smaller than P2, and so on until P is smaller than Pn. Right? If you subtract this out, what you are left with is the most expensive pizza. The only pizza that can satisfy that is that the pizza must be more expensive than any of this. Okay? So that's how you can get the most expensive things. Now this can actually be solved also by the all. So the idea here is that if we use this Pi, there exists Pi such that P is less expensive than Pi, but we do a subtraction here, right? We do a set difference. What it means is that we are doing a negation on this. What it means is that this is equivalent to for all Pi, P is more expensive or equals to Pi. And that corresponds to the most expensive pizza, because the price is greater than any of the other pizza or equal to itself. Okay? And if you want to convert this into the all keyword, this is how you do it. Okay? So again, if we say that the price is P, all the prices generated by this is P1 up to Pn, then what you have is for all Pi, P is more expensive or equals to Pi. Which is again same as P more expensive or equals to P1, and P more expensive or equals to P2, and so on until P is more expensive or equals to Pn. That is basically your most expensive pizza. All right, so let's stop this. Let's stop here. The last part is basically about that kind of universal quantification. The universal quantification is the for all here, but the for all doesn't appear in front. What happens if the for all doesn't appear in front, and how you can try to solve that? It will be slightly heavy in the mathematics. So during the recess, I would advise you to try to revise on your CS1231. Okay? Which will also be beneficial when we talk about functional dependency. Okay, so if you have time, try to revise on CS 1231. Okay, so that's it.
So if team security is questionable,
Huh?
because if there's no, like there's exist no visa dislike by this person, like which means this person dislike all visa, right? It's not like he dislikes some visa, he dislike everything.
Yeah, but if you don't like, you dislike.
I mean the negation of liking some visa is not liking all visa, right?
Yeah, it should be does not like any.